All right. Good. It's working. All right, so welcome everyone to the session on private information retrieval. So this morning we'll have 3 very exciting talks. I'm Pierre, and let's see. So the first talk will be on lower bounds on public key operations in private information retrieval by Jessica and Mohammed, and Jessica will be giving a talk.
Hello everyone. Happy to see all of you here early this morning after the voting. I hope this will be a very simple talk. So this is, I think, hangover friendly. Okay, this is, as David said, lower bounds on public key operations in private information retrieval. I'm Jesko Dimovic, and this guy here is Mohammed Haji Abadi, and we wrote the paper together. Okay, what is private information retrieval? In short, it's a protocol where 2 parties interact, a user on the left and a server on the right. The user has some index, and the server has a database, and the user should learn the database entry at that index. And why is this interesting, or why is it hard? The server looks at the interaction and wants to learn the index, but he's not supposed to learn. And to make it not easy, also the communication needs to be less than the entire database. So if this wasn't the case, the server could just send over the entire database and the problem would be solved. And now, as you can see in the title of the slide, there's like a bunch of adjectives. These are mostly for the people who already know private information retrieval to clarify what we're here talking about. So non-pre-processing, there's no extra steps. We're only talking about a single server. And with non-trivial, I mean that the communication really needs to be only slightly less than the entire database. Usually for private information retrieval, we require it be much less, but because this is a lower bound, it is much more general if we just require this, this slight compression here. Okay, why do we care about this? So first of all, we care about it because private information retrieval with a much more general communication restriction is a very useful protocol in and of itself. And when we prove lower bounds about the weaker version, we also have a lower bound on the stronger version. And then second of all, there's a bunch of other MPC protocols that as soon as they get communication efficient, they kind of turn into a kind of private information retrieval. I don't really want to go into too much detail, but one example here is this string oblivious transfer, where 2 parties interact, Alice and Bob. Alice here is on the left. She has a bit. She's supposed to learn, and Bob has 2 message inputs, M0 and M1, and Alice is supposed to learn exactly one of them. And as soon as the communication is less than both of the strings together, this is already a kind of non-trivial private information retrieval. So if any lower bound that applies to non-trivial private information retrieval also applies to this. Okay, what do we know about non-trivial private information retrieval? I will leave out the non-trivial part because it's repetitive. First of all, it implies oblivious transfer via this transformation by Di Crescenzo et al. Essentially, this is a compression argument. Then it requires public key operations. This kind of follows from the classic results of Impagliazzo and Rudic, because oblivious transfer essentially is some kind of public key. You can use it for some key agreement. Then it does require linear server communication, because if the server doesn't look at the entire database, it knows some information about the index. And all known constructions do require linear public key operations. So we have that it definitely requires public key operations, and we know that it definitely requires linear communication. But the question is, does it really require linear public key operations? So That is the question that we're trying to answer. And sadly, the response is yes. Oh, okay, there was an emoji next to the yes, but I got lost, I guess. Okay, so this is the important slide. This is kind of the technique. And everything else will be kind of interpretation of this technique. So let's look at private information retrieval in the generic group model. So here are the two parties, they are interacting, and the communication is less than n, and the index I is hidden. And because it is in the generic group model, there's an oracle sitting up there, and it has a cryptographic group in mind. And it communicates to the parties via random strings that represent the group elements of this group that they have in mind. And the parties, they only interact with this oracle. You can kind of think of an oracle as this oracle as a honest party that only does this group operations. So now what we observe is that, oh, I already said that. What we observe is that if Alice here, or if the user instead simulates this oracle, then the user privacy stays intact, because essentially you're only protecting against the server, and the server still interacts to an honestly behaving oracle, because the user is simulating that oracle. So the user protects their own privacy. So this red circle is supposed to mean the user simulates this oracle. And now that the user simulates this oracle, I still stays hidden, because the oracle still behaves honestly. But the communication changes slightly. And there's no problem that some server privacy is lost, because we never required server privacy. Okay, so we have this protocol, and now we turn it into a protocol that doesn't have this generic group model oracle anymore. And now, if on the left side we had a server communication that is less than the entire database, and server to oracle communication that is small O of the entire database, then the new communication protocol of this modified protocol is still less than the entire database. And so we removed the generic group model, but we still have a non-trivial private information retrieval. That's the core of this paper. And now let's interpret the results. So we start off with an oblivious transfer protocol that's communication efficient and does slightly less than n generic group model operations. We turn it via this the stuff that I mentioned earlier into a non-trivial private information retrieval. Then with the previous slide, we remove the calls to the generic group model, and then via this paper, Di Crescenzo et al., turn it into an oblivious transfer again. So we removed all generic group model operations, and it is still an oblivious transfer. This is kind of the core of everything, and now I'll slowly extend the result. Yeah, okay. So in many lower bound proofs, you don't only have a generic model oracle, you also have oracle access to some p-space complete problem, so that it is possible to remove all other cryptography, kind of. So essentially, you can think about this p-space oracle as removing all other cryptography except for the generic group model. And here again, Alice only needs to simulate the generic group model to remove it. And what we get is a non-trivial private information retrieval that is secure even with respect to this p-space complete oracle. Okay, so again, let's move through the implications. We turn a string OT into a non-trivial private information retrieval, we only remove the generic group model oracle calls. What stays are the p-space oracle calls. And this is impossible. So this doesn't exist. So, but we can do more. So let's jump back to this slide. Now we add a random oracle. So there's also oracle access to a random oracle. And the same transformation applies. We remove the generic group model, and what only stays is the p-space oracle and the random oracle. And the communication is, everything else still works the same, so which is why I'm fast through the slides. Everything else is the same. And let's walk through this again. We have the OT, turn it into a non-trivial private information retrieval, remove the generic group model calls. What is left are only the calls to the p-space oracle and the random oracle. And then via this transformation, we turn it into oblivious transfer. And now via these results, we know that this is impossible. So essentially, we've showed that like this communication efficient string oblivious transfer doesn't exist in these models. But we can get even more fancy. As you've seen, we haven't used any specific property of the random oracle. So essentially, you can put up here, you can put in any oracle, any scheme that is like efficiently simulatable. For example, the ideal obfuscation. So even if the original oracle has access to ideal obfuscation, but only makes like slightly sublinear access to it, we can still remove this by simulating it, and everything else is still the same. So I don't think I need to say all of this again. All the steps still work the same, but essentially what happens is we start with a string OT protocol that has like access to extremely strong cryptography, but only uses it like not super much. And we remove it, and we get to a contradiction. So essentially, this means that it doesn't exist. So now I want to another way to look at this is through the lens of OT extensions. OT extensions is a protocol that takes a few calls. The goal of OT extensions is to turn a few oblivious transfer calls into many without using much public key cryptography. This is for efficiency purposes. And so essentially what we're going to show is that if you use OT extensions, you will not get communication efficiency in the sense that the communication is less than the two messages together. Okay, so this is an OT extension protocol. It's an OT protocol that makes calls to that makes a few calls to some oblivious transfer ideal functionality. And again, and the communication is less than 2n. Okay, let's walk through this again. We have a communication efficient OT extension protocol. We add an idealized oblivious transfer protocol that can be efficiently simulated in an oracle. And we walk through our steps again, and we arrive at a contradiction. So what this means is, essentially, it is not possible to build a communication efficient OT extension protocol. Okay. That is it. Thank you very much.
All right. We have quite a bit of time for questions. So if you have a question, please come up to the podium.
Sorry, just a quick clarification in terms of what you can capture, since you stated it as a lower bound in terms of public key operations.
Yes.
So does it say something also from non-GGM assumptions? Can I model it there? So if I want to use, say, RSA operations or something like that.
So, why I say public key operations is, let me jump to this slide here. Essentially, anything that you can model as a ideal functionality and you can simulate it just via Oracle calls, you can remove in this exactly this way. So, I mean, it is hard to say that RSA can be thought of as some generic, some Oracle thing. But I mean, if you want to, you can use the generic ring model or whatever, and then you can apply this result as well. And this is kind of what I wanted to point out with this ideal obfuscation. So even if the initial protocol has this extremely strong access to this extremely strong cryptography, we still arrive at a contradiction. Yes.
Are there other questions? All right, if not, then let's thank the speaker again. All right, so let's wait. Great, so our next talk will be on efficient pre-processing peer without public key crypto. This is by Mingxun, Ashujit, and Elaine, and Mingxun will be giving the talk.
Hi, everyone. I'm Mingxun, and thanks, David, for the intro. So today I will talk about efficient pre-processing peer without public key crypto. This is a joint work with Ashujit and Elaine. And so here will be the content today. I will go over some intro background, and then I will give you like a high-level summarization of our work. And then I will talk about one prior work, and our work will build upon this prior work, piano. And then finally, I can get to talk about the contribution in this work. So without further ado, let's get started. The main motivation behind PIR is that information retrieval leaks user privacy. Let's assume we have a user who's interested in the location of EC24. It sends this query to the server, and the server returns it should be in Zurich. And unfortunately, this process leaks the user's privacy because if the server is compromised by an adversary, then the adversary knows that this user should be a crypto researcher. And that's personal information. And there are so many other examples, like DNS lookup actually leaks your browsing history, so on and so forth. So to solve the privacy issue, Choi et al. Back in '95, they proposed this concept called private information retrieval. And the idea is that we need to design some crypto protocol between the user and the server so that at the end of the protocol, the user should still learn the correct result of the query, while the server learns nothing about the query and the response. So recently, there are lots of advancements on pre-IR, and specifically on pre-processing PIR. That's the thing we're going to talk about today. And why? I guess Jessica's talk already gave you a little bit hints, such that in the classical PIR model, there are many, many restrictions. And in fact, there are numerous lower bounds showing that the computation per query has to be linear in the size of the database, which means that for every single query you're going to have, the server is going to scan over the whole database just to answer that single query, which is very, very costly. But in the pre-processing PIR model, we can indeed achieve sublinear computation per query after amortization. So now let's get to see the model we're going to talk about today, pre-processing PIR. That will not be the same as what Jessica has talked about. So we can get around those lower bound. So during the offline phase, it basically means that before the first query begins, the client and the server, they can do some interaction. And they can jointly pre-process the database. Usually we model the database as an array. And at the end of the pre-processing, the client will usually store the pre-processing result. We call it hints. And it usually contains some useful information about the database. Cool. And the hints will usually be used for multiple online queries to help with computation and communication, so that because we repeat it for multiple times, the pre-processing cost after amortization will be pretty low, will be actually sublinear, and also the online cost can be much more efficient. And so if the client is interested in any particular location about a database, let's say it's interested in database X, then because we know that the hint is sublinear in the size of the database, you cannot encode everything inside of the hint. So in fact, the client only needs a little bit extra information for it to recover the database X. So usually we will ask the client to just query a little bit extra information to the server, such that when we combine the hints and the information, it's enough to recover the database X. And we usually carefully design how we store the information in the hint and how we actually ask for the extra information so that we can make the whole process private and efficient. So now let's get to see like the landscape of preprocessing PIR in Minicrypt, so without public key crypto. So previous best work already achieved squared n time per query. That's after amortization and squared n client space, and also squared n communication per query. So that's already pretty good. And in fact, it's actually optimal. The time-space trade-off is actually optimal. So we know that the time times the space has to be at least linear. That's some existing lower bound. So what's left there? That's a communication, right? It's not optimal. So that's what we improved in this work. We improved the communication in the two-server setting to n to the 1/4. And we also improved the single server setting. We improved the online communication of a single server setting to the n to the 1/4, while the offline stays the same. So that summarizes our work. So yeah, now let's get to talk about the technical part. And I will introduce this, this existing work, Piano. This is published at this year's SMP, and this is also one of my paper. So let's get started. And so in Piano, the preprocessing will be like this. So the client will sample some random set, S1 to Sm, and each set will contain squared n random elements or random indices. And the client, it will preprocess the sum of those elements in the database. It will actually repeat this process. It will sample like a lot of sets and compute the sum of them. And then ultimately, it's going to sample roughly squared n log n sets to ensure coverage. Basically, it means that for every single location in the database, it's going to be covered by some sets with high probability. And the client only needs to store the random seed to generate those sets to basically compress the storage and also the sum. And in the second step, the client is also going to preprocess some random elements. So you can think about the client just remember a subportion of the database. Cool. And now let's get to see how those things can help with the online query. So assume the client is interested in a database location X. So the extra information it needs to recover this X is actually the sum of S minus X. But that's actually not private to directly ask the server about this, because it actually leaks the information that all the elements in S minus X would not be the current query. So the solution of Piano is that we simply replace X with a preprocessed element Y here. And we simply ask the server about a sum of S minus X plus Y. And by learning S minus X plus Y, it's actually enough for the client to learn the value for X, because the S is known, Y is known, and just solving the equation, we can get X. And also, this is private, because from the server's perspective, this set looks random. And so in this talk, we focus on the online communication cost. And in Piano, the communication cost will be about representing this set of S minus X plus Y. And in the previous work, they simply write out all squared n elements in this set. That results in squared n communication cost. So can we improve this? And now let's get to see our improvement in this work. So what's the challenge out there? Well, the first step is how do we actually represent a random set as before we do like before we do the editing. So in Piano, we already use pseudo-random sets based on pseudo-random function. You can think about we just use a pseudo-random function 1, and it generated an offset in the database, and you can keep going. But after programming, that's the tricky point, that we don't actually have like a good way to represent it based on like usual PRF. So Piano just write out everything. But there exists something called privately programmable PRF that allows you to program some point on the PRF. So this is privately programmable PRF. So we start with the K, that's a usual PRF key, and you evaluate to some roughly D pseudo-random values. But we specifically focus on one new operation that is called programming. It means that we want to program the ith location from X to Y, such that we result in a new key, K prime, where all the evaluation stays the same. The only thing changed is the ith location, where we change X to Y. And the privacy requirement says that the new key, K prime, leaks negligible information about the programming location. So something like this actually exists, but they are quite tricky to construct. And there are numerous prior works on this, and they're already used by PRL schemes before. And they do have a lot of good things. For example, they do support a pretty large domain. They have polylog program key size. But the downside is they do require stronger assumption like LWE, and they are relatively complicated, and there's no good implementation. So in this talk, I'm going to introduce privately programmable PRF with list decoding. This is a simpler construction compared to existing works. And we don't have polylog program key size, but we have skirt-D program key size, and it's from PRF, and it's simple. And what do I mean by list decoding? Well, I guess it'll be clear once I get to those following slides. So before the programming, how the key looks like. So we have a key K, and then now we want to evaluate this original key. It's before the programming. So we assume an underlying PRF G, such that in the first step, we are going to use this G to stretch this key K to skirt D intermediate keys. So to the stretching, you just evaluate G, K at 1 to D, so 1 to skirt D. And then in the second step, for each intermediate keys, we're again using the underlying PRFG to stretch it to skirt D pseudo-random values. And then finally, we call the underlying, basically the last level of this G, FK1 to FK. Basically, that's the whole domain evaluation. So that's before programming. And why do we need this two-layer construction? That's because in the programming, we need it. So now let's get to see an example where we want to program the fifth location from X to Y. So all the relevant information in our programming will be all the intermediate keys and also the special block around the fifth location. That will be the second block here. And then we first collect all the relevant information. And then here's the important part. How do we programming? So we will basically change the key corresponding to that specific block with the random intermediate keys. And then we will replace X with Y. So that's how we do programming. And then we call these things our program key K prime. So this program key K prime, it includes skirt D intermediate keys and also skirt D like pseudo-random values. And you can clearly see that the size of it is skirt D. And the privacy of it is actually pretty straightforward to prove. And the tricky part is, how do you actually evaluate this key K prime? So we call it list decoding because when you evaluate it, it could result in multiple cases. So from the evaluator's perspective, it doesn't know where you program the point. So what it can do is it simply place the program block in every possible location. For example, in the case one, it placed the program block in the first block and use the remaining intermediate keys to generate the remaining blocks. In the second case, it will place the block in the second one, and that's the third case. So from the evaluator's perspective, it doesn't know which case is correct. So in total, there are skirt D possible cases, but from the key generator's perspective, it knows that one of them will be the correct one. So that's what we mean by list decoding. And it also has a very nice overlapping property that each location only has two different evaluations instead of skirt D. Although for the whole domain, when we look at all possibilities, there are in total skirt D possible cases, but each location, they will either determine by the intermediate keys or the special block down there. So each location has two different evaluations. That gives us a really nice OD time algorithm to compute all cases. So how do we use that in our PIR? So by simply just replace the upload with our program key. So now we are basically using a PRF to generate like a domain skirt and set random set. So basically we just use a program key of size n to the 1/4. That's like skirt n, skirt n. So that's n to the 1/4. So we upload this program key to the server. The server computes all the possible cases and returns n to the 1/4 possible set sums to the client. And the client can pick up the right cases, the right case. So that'll be it. Essentially, that's the core idea. But that's only for a single query. And we realized that actually handling multiple queries is trickier than we thought. So in our paper, we proposed 2 new strategies to handle multiple queries. So we do have a strategy 1 that's simple. It uses the PPPRF as a black box, but it results in lambda times blow up in the cause, which means that instead of sending 1 key, you need to send lambda keys to the server. And we do have a strategy 2 that opens the box of the construction, but it does only have constant overhead. So that's better. But why do I want to bring up this strategy 1 is we do have a side product that we realize that our strategy 1 can combine with other existing PIR query structure. For example, we can combine tree PIR. And the result will be a polylogarithmic online communication single server PIR with DDH or LWE. So it's not in Eurocrypt, but that's a pretty nice result. So it's not a new feasible result, but it's actually conceptually simpler compared to existing polylogarithmic, like single server preprocessing PIR. Cool. We indeed have implementations. I forget to put the slides here. But for the future, there are already many recent developments on this paradigm. For example, someone improved the concrete performance. Someone adds verifiability. And a new work improves, they actually incorporate dynamic updatability in this paradigm. And there are some applications we are excited about. For example, we do have an ongoing work developing a private searching application. And there are other applications like private blockchain node and also like password bridging alerts, stuff like that. So I think that'll be it. Thanks for listening, and I'm happy to take questions.
Great. So we have quite a bit of time for questions, so please come up to the microphone.
I had a question on the result. You mentioned 2 server and 1 server. I was wondering, why do you need 2 servers?
Oh, that's because that's about how do you do preprocessing. So in the 2 server setting, you can require one, we call it like a preprocessing server to actually just give you the actual server can just preprocess the thing and then provide a hint to the client. In the single server setting, you need to use some extra technique. So that's more costly.
So you're requesting the server for some information. It's not a streaming database setting.
No, that's only for the single server setting.
Oh.
The 2 server setting, you don't do that. You just ask the server for preprocessing.
I see.
All right.
Thanks.
Other questions? So I have one question. So in your single server construction, right, in the offline phase, do you still have to stream the database?
But it's not like the main point of our work here. So we basically just incorporate like existing strategies for preprocessing.
I see. But if you start using public key, like when you talk about your tree peer composition, do you still have to stream the database in the offline phase, or can you also?
So yeah, in that case, you can actually just use FHE or stuff like that. But you can also like use streaming to avoid like the conceptual complexity. But
I see.
It's up to you. Yeah.
I see. Okay. Yeah. So using public key operations, you can get sublinear communication in the offline.
Indeed. Yeah.
I see. But with one-way functions, are you limited only?
No, with one-way function, you have to use like the streaming thing.
I see. There's a lower bound for.
So there's some new results from Elaine, but I'm not sure I can talk about that here.
Oh. Okay. All right. Future work. All right. Other questions? All right. Let's thank Mingxin again. All right, great. So our final talk for this session will be on efficient and generic methods to achieve active security in private information retrieval and more advanced database search. This is work by Ryo, Kaoru, and Koji, and Ryo will be speaking.
Thank you for the introduction. I'm Ryo Eriguchi. Today, I'm going to talk about efficient and generic methods to achieve active security in private information retrieval and more advanced database search. This is a joint work with Kaoru Kurosawa and Koji Noida. So first, let's recall the concept of private information retrieval, or PIR for short. In this setting, a server has a database and a client has an index X. And the goal of PIR is that the client gets the X entry of the database without revealing the information on the client's query. So in this setting, we do not consider the privacy of databases. So in this study, we consider a more general setting where servers have function f, and then a client has an input to f. So the goal is then the client obtains f of x without revealing information on his input x. So this is a generalization of PIR, because if we set f as the function that takes an index as input and outputs the data item corresponding to the index, then this is equivalent to a PIR. So this generalization allows us to consider more advanced queries, such as keyword search. So for PIR, or more generally for secure database search problems, we have a trivial solution where the client downloads the entire database and performs search locally. This is secure, but this is not efficient, because the client-side computation and the communication complexity are proportional to the size of a large database, right? So therefore, we aim at protocols whose client-side computation and the communication complexity are much smaller than the database size. So traditionally, there have been two settings for secure database search problems. The first one is a multi-server setting, where more than one server share a function f, and an adversary corrupts a bounded number of servers. The other one is a single server setting, where only one server is available. So typically, protocols in the multi-server setting can achieve better efficiency, and also protocols can be constructed from weaker assumptions or even unconditionally. On the other hand, in the single server setting, a client typically needs to perform heavy computation, such as public key operations. And also, protocols need stronger assumptions. And in particular, unconditional security cannot be achieved in the single server setting. So in this work, we focus on the multi-server setting. Okay, so a basic security notion for secure database search problems is passive security, where an adversary an adversary learns information by corrupting servers, but the adversary follows the protocol instructions. So in this setting, there are some efficient protocols. For example, for PIR, we have computationally secure PIR protocol based on function secret sharing, which can be instantiated from one-way function. And also, we have an unconditionally secure PIR protocol with 3 to T servers. So second, for polynomials, even for polynomials, we have an unconditionally secure database search protocol. And also, recently, computationally secure protocol with a smaller number of servers was constructed from sparse LPN. And finally, we also have an unconditionally secure protocol for computing constant depth circuits. However, all of these protocols are not actively secure. That is, if servers send incorrect messages, then there is no guarantee that a client obtain a correct result. So in this work, we consider active security, which requires that which guarantees the privacy and correctness, even if corrupted servers may deviate from a protocol. More specifically, the privacy requirement is almost the same, but the difference is that corrupted servers learn no information on the client's query, even if corrupted servers introduce adversarial errors into their messages. And a technically more difficult challenge is to achieve Byzantine robustness, where a client, which requires that the client output is correctly f of x, even if servers return incorrect messages. So there is a related security notion called verifiability, but verifiability is a weaker security notion than Byzantine robustness. So more specifically, verifiability guarantees that a client never accepts an incorrect result, but it does not guarantee that the client can uniquely determine the correct output. So that's the difference. So to obtain actively secure protocols, there were compilers from passively secure protocols to actively secure protocols. So more specifically, Baimel and Stoll showed that a passively secure K-server protocol can be transformed to an actively secure M-server protocol, while the number of servers increases by 2 times t. And recently, it was shown that the number of additional servers can be reduced to t. So, however, these compilers are not satisfactory because the overheads in the client side and the client-side computation and the communication complexity are exponential in the number of corrupted servers. So, therefore, if the number of corrupted servers grows, then these compilers do not work efficiently. And also, these compilers were only applied to PIR protocols. So then it is natural to ask for a compiler for even more general functions than PIR, such as polynomials or constant depth circuits and so on. So now we show our results. In this work, we propose generic and efficient compilers from passively secure database search protocols to actively secure protocols. So our compilers are generic in the sense that our compilers are applied to any passively secure protocol for computing even more general function than PIR. And also, our compilers are efficient in the sense that the overheads in the client-side computation and communication complexity are only polynomial in the number of servers. So, on the other hand, as a trade-off, our first compiler requires m² rounds of interaction between the client and the servers. And so to overcome this drawback, we also present another compiler that needs only 1 round of interaction. In this case, however, we have also a larger number of servers are required. So there is a trade-off. So now we move on to the technical details of our compilers. So in this talk, we focus on our first compiler. So please see the paper for further information on our second compiler. So our first compiler transforms a passively secure K-server protocol into an intermediate protocol, which we refer to as a conflict-finding K-server protocol. And then we construct an actively secure protocol based on this conflict-finding protocol. So what is the conflict-finding protocol? So the privacy requirement is the same. That is, the corrupted servers learn no information on the client's query. So an important property is that the conflict-finding property, so which requires that if servers are malicious, then the client outputs a correct result, in which case nothing is a problem, or so the client outputs a partition of the set of servers, such that the set of honest servers is included in one of the 2 parts. So for example, if the 3rd and 4th servers are malicious, then the conflict-finding property allows the client to find a partition of these 4 servers such that the honest server, all the honest servers are included in the same group. So in particular, if we choose two servers, one from G0 and the other from G1, then at least one of them is necessarily malicious, right? So we call such a pair of servers a conflicting pair. So this is a core idea of our algorithms. So in this talk, we explain how to obtain an actively secure protocol based on conflict-finding protocol. So please see the paper for our construction of conflict-finding protocol based on passively secure protocol. So towards that, we suppose that there are M servers and T out of them are malicious. So then the number of honest servers is M minus T, which is equal to K. So the K is the number of servers in a given passively secure protocol. Okay? So then ideally, if a client can find the set of all honest servers and executes a K-server protocol with them, then the client will obtain a correct result because responses are computed by honest servers. However, the passively secure protocol itself cannot help the client to find the set of honest servers. So therefore, our strategy is to find as many conflicting pairs as possible based on the conflict finding property, and we let the client determine all the K honest servers, and then the client will execute a protocol with them and obtain a correct result. So toward that, we consider a graph whose nodes represent servers. And there is an edge, if and only if the corresponding pair of servers is not found to be a conflicting pair. So initially, we have no conflicting pair, so the graph is set as a complete graph. So then our algorithm works as well as follows. So first, the client finds any connected subgraph of size k. In this case, k is 3. And then the client executes a conflict-finding protocol with servers in this subgraph. So the conflict-finding property allows the client to find a partition of these 3 servers. It is important that all the honest servers in this subgraph are included in the same group. So therefore, if the client chooses any edge crossing the groups, it is a conflicting pair. So that is one of them is malicious. So the client can always choose such an edge because we suppose that the subgraph is connected, right? So then the client removes that edge and the graph changes like this. So in the next iteration, the client again chooses any connected subgraph of size k and executes a conflict-finding protocol with them. And the client will obtain a partition of the set of servers like this. So again, the client chooses any edge crossing the groups, which is a conflicting pair, and removes that edge. So because the rest is just repeating this process, we skip the details. So chooses any connected subgraph and executes a conflict-finding protocol with them. And so it chooses any edge crossing the groups and removes that edge. So and so on. Okay. So finally, after sufficiently many iterations, we reach a state where the only remaining connected subgraph of size k consists of honest servers. So right, so edges between. So this is because edges between honest servers are never removed. This is because so honest servers are always included in the same group, but a client removes an edge crossing the groups. So therefore, edges between honest servers are never removed, and the subgraph consisting of honest servers remain fully connected. So now the client will execute a protocol with them, and so he will output the correct result because protocol are involved with honest servers only. Right? So this is our algorithm. So now we summarize this talk. In this work, we consider secure database search problems, and we propose generic and efficient compilers from passively secure protocols from actively secure protocols. Our compilers are generic in the sense that our compilers are applied to any passively secure protocol, so for computing even more general functions than PIR. And also, our protocols are our compilers are efficient in the sense that the overheads in the client-side computation and communication complexity are polynomial in the number of servers. However, as a trade-off, our compilers require multiple rounds of interaction or a larger number of servers. So there is a trade-off. So then it is natural to ask, can we get the best of both worlds? That is it possible to achieve constant rounds or ideally only one round while keeping the number of servers as small as possible? Okay. So here is the list of references. This is the end of my presentation. Thank you.
Great. We have time for questions, so please step up.
Hi. First of all, thank you for the talk. I have one question about the removing edges part. Could you maybe go back to those slides?
Okay. Here.
So when you do maybe one more.
Okay.
So when you do these partitions, you basically get the partitions through the conflicting pair or through the conflict finding protocol. Is there a reason why you only remove one of the edges between the partitions instead of all of them at once?
I see. So if you remove more edges, then the algorithm will finish more faster. But so in the worst case, the asymptotic computation complexity does not change even if you remove the edge, because an adversary can only introduce an error to this server. So instead of so the client, so that the adversary can let this server behave honestly, so not to be detected as malicious. So then, the edge can be removed is the only one. So you cannot remove the multiple edge. So yeah, it does not affect the asymptotic computational complexity. So thank you.
Are there other questions? If not, let's thank Rio again. Thank you. And this concludes the session.